Okay, here's a picture of the domino, and I'm modeling the domino just by a straight line. Okay, I assume it's a completely thin domino. It isn't a completely thin domino. Okay, that makes a difference, and a lot of you noticed that there's a difference. Okay, when the domino, now the domino is going to fall, and the other thing we're assuming is that the domino, the base of the domino doesn't slide during the fall. Now there are two reasons it might slide. One is, if you get down to here and let it go, it's probably going to try to slip out here if it's on a smooth surface, right? Another is, it's moving this way, it's got momentum in this direction, so it might move this way, okay? So all that's pretty complicated. The other thing is, it does have thickness, so it's got to go to a certain angle before it starts to fall. And then it pivots around that side, and that causes complications that I'm not going to talk about, okay? So, what we do say, and what's on the handout that I'll run over and get shortly, it's going to follow, the top of the domino is going to follow an arc of a circle. Since it's not slipping, and since the domino doesn't change length, this end is going to follow the arc of a circle, because this end is always going to be at the same distance from this point. So this point's going to be the center of the circle. Everybody understand that argument? Okay? So, let's just put the domino here. Now, how are we going to measure the position of the domino? We could measure the position by how high this domino, this end is off the table, how far it's moved from here, okay? But the most convenient measure of the position is going to be the angle it makes with the tabletop. So I'm going to call that angle theta. Make sense? Okay? Now you might or might not know some trigonometry. But we're not, I'm going to give you the result that you would get from the trigonometry, and I'm going to assume you know the trigonometry. And I'm not even going to explain too much why this works, although I will say that the domino is symmetric about its center. So the force that's causing this to fall is a gravitational force that can be considered to act at the center of the thing, so it's like you've got a force pushing down on it here, okay? And the closer it is to the tabletop, the more effective that force is going to be in speeding it up, okay? When it's up here, it's like I'm pushing on this door. Now, I'm not pushing this way. Everybody see what I'm doing? I'm pushing straight out toward the hall. If I push straight out toward the hall, the door is going to move, right? Yeah. Okay, and if I was pushing at the center of the door, it would be the same thing. Now, if I push with the same force when the door is here, it speeds up a lot more than it does if I push when it's out here. Yeah. So what's happening is very much analogous to that. But the push is gravity pulling down. Gravity can be considered at the center here and all that stuff. And then you get into physics of torques and angular moments of inertia and angular accelerations. And I'm going to bypass all that because that's tough even if you're 2 months into a good physics course, okay? That's where it gets tough for people. So, bypassing that, I'm going to say that the rate of change of theta with respect to time is proportional to, and it's directly proportional, well, it's going to be directly proportional to this distance right here. Okay? That means if you were to double this distance by letting the angle change until things about here, theta would change twice as quickly, and actually what I just said is wrong because I left something out. I said that absolutely wrong. Not the rate of change of theta, it's the rate of change of the angular velocity. Angular velocity is just how fast theta is changing. And it's really a measure of how fast that door is moving or that domino. Okay? Don't have to worry about that or what it means or the physics of it. But I'm going to say that rate of change of angular velocity is directly proportional to, I'm going to call this distance x. Okay? Which is directly proportional to the cosine of theta. Now, I don't assume that you know any tricks. Some of you know some because you saw some in geometry and so forth. But we're not going to develop the trigonometry, but it's very straightforward trigonometry to understand that this distance is proportional to the cosine of theta just by the definition of the cosine. All you need to know is you have a cosine button on your calculator. And if you type cosine into Excel or Wolfram Alpha, it's going to calculate the cosine. So this is just something that you can calculate without understanding it at all. If you understand it, and we'll talk a little bit more about what that means, just so you have that as a reference, because some of you are in a position where you could understand it, you'll be able to calculate that, okay? Which means, well, let's see, if you know the angle, what can you calculate? Give you a hint, I just told you.
You know the angle,
You know the cosine. You can calculate the cosine of theta, right?
Yeah.
Well, if you can calculate the cosine of theta, then you've calculated what? Well, it's going to lead you to be able to calculate x. Okay? Although you don't need that because the rate of change of angular velocity is proportional to x, which is proportional to cosine of theta. So, the rate of change of angular velocity is proportional to cosine theta. Now, on the sheet I'm going to give out, and all I'm trying to communicate here, you're not going to sort out all these ideas or how they relate until you work on them a little bit. What I'm saying is that we have this really important rate of change that's proportional to something that you can see on a picture that's proportional to the cosine of theta. Okay? What does it mean for something to be proportional to something? Remember we did this thing on proportionality and proportionality square and inverse proportionality? I haven't asked you a lot of questions about proportionality. It's been a couple of days. I'm sorry. Go ahead, Cindy.
it's like, if it was meant to be in a fraction, like, it would be in the same, factor.
Okay. So,
You know,
let me write it down.
y equals kx.
Yeah, it's like y equals kx, right?